In this book, we have mostly been looking at program graphs and memories. This chapter on model checking, however, looks at transition systems. So let's take a closer look into how program graphs and transition systems relate. We already said that the configurations that we looked at before, the pairs of a node in the program graph and a memory, correspond to the states, and that the execution steps are the ones that give rise to transitions. To be more concrete, let's take a look at this program graph. It has 4 nodes. Initial node A, final node D, and 2 other internal nodes B and C. We can move from A to B in case x is greater than 0 and move back by subtracting 1 from x. We can move from A to C in case x is less than 3 and move back by adding 1 to x. And while the program graph appears to have an edge from A to D, the label on it is false, indicating that in the semantics we'll never take this edge. Assuming that x can take values 0, 1, 2, and 3, there will be up to 16 possible states in the system. That is 4 coming from the 4 nodes in the program graph, 4 coming from the 4 values of x, and 4 times 4 is 16. However, we know that the initial state is A and that the initial value of x must be one of 0, 1, 2, and 3. And so the only states that are actually reachable will be the 10 states listed here. Next, let's try to define some atomic propositions that are useful for expressing properties of the program. We have 4 using the at symbol, at A, at B, at C, at D, telling for a state which program point we are at. And we have 4 labeled #0, #1, #2, #3, telling for a state what is the value of x. And then we have an indication of whether we are at the initial node or whether we are at the final node. In this case, of course, the initial node is A and the final node is D. And the labeling function makes our intentions clear. We are saying that if we are at A and N, then the labels are we are at A, the value is N, and that's the initial node. And similarly for the other 3 cases. So the property AG not at D expresses a property that we already talked about, that the program point D is in fact not reachable from the point of view of the transition system. The formula at C and #2 implies always in the next step at A and #3 says that whenever we are at the program point C with the value of x being 2, whatever we're doing in the next step will end up at the program point A and x will have the value 3. For the general construction of how to go from a program graph and a set of memories to the transition system, let's first recall what it is we need to define. What is a transition system? That is summarized here. For the general construction, we proceed as follows. The set of states will be the set of configurations, that is, pairs of nodes in the program graph and memory sigma. The initial state will be those configurations where the node is the initial node. Then we have a transition whenever we have an execution step in the semantics. The action alpha being performed is not being recorded in the transition system. And then we have propositions that can be used, that we are the node Q, that the memory is sigma, that we are the initial node, and that we are the final node. And the labeling function is being set up in such a way to make these ideas precise. However, the way we defined it here, transition system may be infinite. To avoid that, we have to restrict our attention to a finite set of memories. Let us try it out on the factorial program that we have listed here and look at some properties we can express in the logic. The first formula says, when you are the initial node, it is possible to go to the final node. That is clearly true for this program. The second formula says, when you are the initial node, regardless of how you execute the program, you will end up at the final node. That is also true for this program. And in fact, for a deterministic program, the answer to the second and the first question would be the same. The third formula says, whenever you are at the initial node and x is 7 and y is 0, regardless of how you run around in the program, you will end up at some point at the final node with x being 0 and y being 5040. This is what says that the program correctly computes the factorial of 7 to be 5040. For a more manageable setup, we are going to restrict x to be at most 3 and y to be at most 6. What is the greatest number of states that there can be in such a transition system, and how many of those will be reachable? And determine whether or not the formulae that once we are the initial node means that eventually we end up at the final node, and once we are the initial node there is no void to avoid ending at the final node, whether or not those are true. Having done that, you should read the section in the book during the try it outs on the way.